We have been discussing various methods of bivariate analysis. The first main method that we had a look at was correlation. We mainly covered two correlation coefficients, the Karl Pearson's coefficient of linear correlation. Always remember that Karl Pearson's coefficient tries to measure the degree of linear association between the pair of variables that you have at hand. And we also did a learned about the Spearman's rank correlation test, which is based on rank differences rather than the actual values of the two variables, right? And we did note that Spearman's rank correlation is very useful for looking at correlation between qualitative characteristics to study whether there is a relationship between them. Now, if you remember, we had discussed about the various reasons why a pair of variables could exhibit high correlation, and one of them was that there is a cause and effect relationship between the two variables at hand. The examples that I quoted even then was price and quantity demanded. Changes in prices cause changes in quantity demanded as a response, right? So if there is a cause and effect relationship between the pair of variables you have, you will find or you will see that it has a high degree of correlation. However, that is not the only reason why you may have a high degree of correlation between your variables x and y. It could be that there is a third variable or another common factor that is driving or that is causing the changes in both the variables that you have with you. And therefore, you could have a high degree of correlation even if the variables were not having a cause and effect relationship between each other. Now, regression explicitly, when you talk about regression analysis, you're explicitly dealing with and studying cause and effect relationships between x and y. So, if you're regressing the variable y on x, you mean to say that you suspect that there is a function of this sort where y is your dependent variable, which is being variations in which are being determined by variations in the x variable. Remember, these x variables are called explanatory variables or independent variables. Okay, these explanatory and independent variables, the names are interchangeably used. So, when you regress y on x, that is when you are entering into the field of regression analysis, you are saying that changes in y are caused by changes in x. So, you are talking about a cause and effect relationship between the two variables. On the other hand, correlation does not assume a cause and effect relationship. It is just simply measuring the degree of linear association. There might be a cause and effect relationship, or there might not. There might be some other reason why they are very strongly associated to each other. Now, the regression can be regressing y on x, or you might even have another possible function if you have a pair of variables x and y, that is, you could regress x on y. So regressing x on y means x is being explained, or variations in x is being explained by variations in y. Okay, so both these equations are inverses of each other. Okay, now remember here, if you're regressing x on y, that is the variable on the left hand side is x, that means x is your dependent variable. And you're saying that variations in x or the changes in x can be explained to a large extent by variations in y, which is, in this case, y is your explanatory or independent variable. Please do get used to the terminology. Regressing y on x means Y is the dependent variable. Regressing x on y means x is the dependent variable. Now at this stage, we are only going to deal with two variable regression models. That is, you have one dependent variable obviously, and you have only one independent or explanatory variable. We are not going to go into more details of multivariable regression models. That is all left for basic econometrics elective in semester 6, I think, for you people. Okay, so we will simply deal with two variable regression model where you have two variables x and y, and you're looking at the cause, or you're studying at the cause and effect relationship between two. So every time you have a pair of variables, there are two possible regression equations you can associate it with. It could be y on x, or it could be x on y. Right? Now what does regression mean? Regression means, I think the best way to explain it is to say that regression is an average relationship between the two variables that you have, x and y. So if the average value of x is given to you, when you're regressing y on x, if the average value of x is given to you, you can find an average or expected value of y. Remember, if you're regressing y on x, like I said, y will be a function of x, and we are dealing with perfectly linear regression relationship. So I can write it as y is equal to a plus b times x. Okay, so when you are conducting or estimating or performing a regression analysis on the variables x and y, and if you choose to regress y on x, you're basically trying to determine this function. How is y linearly related to x? That is, you're trying to find the values of the parameters of this function. The parameters are a and b. What you have with you to find a and b are values of y and x. You have several pairs of observations of x and y, and you're regressing y on x means using those observations, you're trying to calculate the value of a and value of b. Okay, just note that when I was discussing the OLS method and I was talking about the normal equations, I think I wrote y is equal to ax plus b. Okay, now slight change in the form. Here I have made a as the constant. In fact, in the regression equation, this is the intercept term. Okay, and here b is the slope. Okay, slight change, but you're still dealing with a linear equation. The reason I'm doing it is by convention, we generally use the letter B of the English alphabet to represent slope, especially when you're discussing regression analysis. So it's easier for me, which is why I have written the linear equation as a plus bx. Okay. Now, like I said, this average relationship can be in two forms, regressing y on x or regressing x on y. So if you're regressing x on y, like I mentioned earlier, you mean that x is a function of y. Again, we are dealing with right now only perfectly linear regression relationship. So x is a function of y, as in x is a linear function of y. So a dash plus b dash y, since y is the explanatory variable. Once again, b dash and so on, I'm preferring to use the letter b as the slope. Okay, this is just to make things easier for me. Okay, even if you do change the letters, nothing happens. Just be consistent with whichever method you are using, or rather whichever symbol you are using. Okay, so now how do we go about estimating these relationships? you have already actually learned that you can regress, or you can find the regression equations based on the principle of least squares, which we already covered. Just in the last few lectures, we looked at what the principle of least squares means, and how that leads us to two normal equations for the linear function. Remember, for a parabolic function, if you're trying to fit a line of best fit based on the principle of least squares, we had three variables or three parameters to be found out, which is why we had three equations, three normal equations. So we estimate these regression equations, or they are called regression function, based on the principle of least squares. It is also called the ordinary least squares method or criteria, based on ordinary least squares criteria, which, like I said earlier, is based on the fact that you are trying to minimize the sum of error terms squared. And what is these error term? Error term is the deviation. Ui is the error term. It is also often called the disturbance term. And another word for it is the deviation. It is also known as the deviation. Now, deviation between the observed or actual yi and the estimated yi. I call it yi hat. Now, what do I mean by estimated yi hat? Remember, regression talks about an average relationship. So if you manage to successfully fit the regression line yi is equal to a plus b xi, using whichever principle that you have used, what you will succeed in doing is you can predict or estimate the average value of y for any given x value. So, which is why regression is called as the relationship between averages, or the average relationship between the dependent and the independent variables. So, once you have estimated a regression function, given any value of x, you will be able to estimate an average value of y. That is, on an average, your y value will tend to be what is predicted by this linear equation, this regression function. However, often due to circumstances beyond our control, or due to influences outside of the explanatory variable, what happens is your actual yi differs from the estimated yi hat. I should probably put a hat to no need of hat here. Okay, the observed yi differs from yi hat. If you remember the diagram that I drew last time, here you have your x variables, here you have your y variables. Like I said, you probably have pairs of x and y variables. Now, based on these pairs, if you try to estimate an average relationship, you can probably get, based on this hypothetical distribution of observations, you can probably get a line of best fit or a regression function y is equal to a plus bx, right? So given that the x value is something like, let me just make this, okay, let me put it in terms of crosses. Right, looks pretty. So what the regression function tells you is, given the value of x as say x1, your average value of y will tend to be y1. However, as you can see here, the actual y1 hat, okay, I'm calling it y1 hat because that is the one based on the estimated regression function. So, but the actual observation for x1, you notice that you have actually got y1 without the hat. So the deviation between this observed and the estimated value is what I'm calling as u1, or the deviation or the error term or the disturbance term. Now if you have the entire population with you, for the same value of x1 there are probably many y values that can be recorded, and this y1 hat is supposed to be give us an idea about what the average value of y given the value of x is equal to x1. That is a general idea behind regression, that the estimated sample regression function. We are estimating a sample regression function simply because we do not have the entire series of observations related to the population given to us. We only have a small slice of the population, a sample of the population. And based on these observations, you can estimate this regression function. So, like I said, your error term or your deviation term is observed yi minus the estimated yi hat, and you need these deviations to be as minimum as possible so that your estimated regression function represents the actual population regression function as best as it can. And the criteria for that is given by a principle of least squares, which says minimize the sum of these deviations squared. Okay, so minimize summation ui squared or minimize u square. So since we have not done too much of differential calculus, we do not care about the derivations right now. All you need to remember is, like I said in the principle of least squares, this regression function can be solved or can be estimated using the two normal equations. Remember your normal equations, your function or your regression function, if it is a plus b times x, you will have two normal equations, which is normal equation 1 will be summation operator to the original equation, so summation y is equal to n times a plus b times summation x, and your second normal equation is summation operator applied to xy, that is x times y. So xy is equal to x times, this will be ax plus bx square. So a times summation x plus b times summation x square. Now based on this, when we were fitting a line, we took these two normal equations, we filled in all the possible values from the table we had at hand, and then we just solved simultaneously to get the values of a and b. Since we're doing regression analysis, I'm just going to derive the two values in form of a formula. So for b, I can write it as summation xy minus summation x by n, summation y by n, that is x bar and y bar. Oh, no. Sorry. Let me just edit that. Okay, you'll get summation xy, summation x into summation y divided by n whole divided by summation x square minus summation x whole square by n. You can either remember this formula or we can make it a little bit more easier to remember. That is, if you take the LCM of the on the numerator and the denominator, you can write this as this: n times summation xy minus summation x into summation y whole divided by n times summation x square minus summation x the whole square. So this is the value of b, or the slope term, and the value of a can be calculated simply by y bar minus b times x bar. Okay. So you can remember the formula for b in either of this format, whichever you find simpler, and this is the formula that you have to remember for a, right? Now remember, my original regression function that I tried to estimate was y equals to a plus bx, and if I substitute a is equal to y bar minus bx bar into this equation, I'll get y is equal to y bar minus b times x bar plus b times x. Taking y bar that side, I'll get y minus y bar is equal to b times x minus x bar. So y minus y bar is deviation of y from mean value. X minus x bar is deviation of x from its mean value. Here b is called the regression coefficient of y on x. Remember, it's always dependent variable on independent variable. So you can even write this for clarity as y minus y bar is b times yx. Regression of y on x, b yx times x minus x bar. Okay. So remember, when you are regressing y on x, your regression coefficient is byx. I would like to draw your attention to one more relationship. Remember your byx, the formula that I told you was n times summation xy minus summation x into summation y whole divided by n times summation x square minus summation x the whole square, right? Now if you divide the numerator and the denominator by n square, okay, dividing by n square in both numerator and denominator. Okay, I'm not writing that whole. Okay, what you will get is b times yx can be written as summation xy by n minus summation x by n into summation y by n. Similarly, this can be written as summation x square by n minus summation x by n the whole square. I hope you understood where we are going. So this can be written as pxy divided by sigma x whole square. Okay, by similar logic, if you are regressing x on y, you can represent your regression equation as x minus x bar is equal to b times y minus y bar, where b here would be b dash, right? B dash, or let me just call that the regression coefficient of x on y. X on y means my original equation was x is equal to a dash plus b dash y, right? So I can represent this that as x minus x bar is equal to bxy, that is regression coefficient of x on y times y minus y bar. Same as above, this regression equation bxy, the formula will be given by n times xy minus summation x into summation y. It's the denominator that changes. In the denominator, you will have n times summation y square minus summation y the whole square. And once again, if I divide it by n square throughout, I can write this as summation xy by n minus summation x by n into summation y by n whole divided by summation y square by n minus summation y by n the whole square. As you can see, the denominator is your sigma y square because it is mean of y squared minus the mean squared. Yeah, so that is your standard deviation, your variance formula. So byx can be written as, again, if I call the numerator pxy, very related to your correlation coefficient pxy, not exactly that though, divided by sigma square y, that is variance of y.